there's a lot of different ways to factor. We're going to look at a couple special cases today. The first type of factoring we're going to do in our goal to just cover the basic types of factoring today. We'll look at all the special fancy circumstances on Monday, but today we're just going to do the basics. Today I want you to be able to factor out the greatest common factor from an expression. We've touched on that in a couple of examples, but we haven't really done much of it. We're going to factor expressions that are the difference of squares. If you have a binomial, two-term polynomial, each term is a perfect square and there's one is subtracted from the other, it'll factor. And the third thing that we want to take care of today is we want to be able to factor all different types of trinomials that are factorable anyway. Well, first of all, what does it even mean to factor? Basically taking it apart into its pieces. Just like you can factor the number 10 into its 2 primes, 2 times 5. You break it into its pieces. And then there's a lot of things you can do once you've got an expression broken into its pieces. And so that's kind of what we're going to turn to. Another word for factoring really is undistributing. We're basically reversing the distributive process that we did probably better than a month ago now. First of all, we're going to look at the case of a greatest common factor. If you've got an expression and all the terms have some common factor, we can rewrite it and undistribute. Instead of putting a common factor into each term, we can factor it out. And up here, we saw this, like I said, better than a month ago now, but the distributive property says that if you have a times some expression, you can multiply each term by that a. Well, now we're just going to reverse that and say that we can factor it out and put it out in front of parentheses. Well, we're just going to take that and look at a few examples, some that are pretty straightforward, some that take a little bit more insight to see what those common factors are. All right, well, let's start with a real basic one here. Let's factor this expression. There are 3 or 4 general ways to factor. And you kind of have to be searching for all of them, but the first one that you always look for is greatest common factor. You always look in any expression that you want to factor, you always look for the greatest common factor first. 1, because it's the most basic kind of factoring, and 2, because it makes other factoring easier. So let's take a look at this expression. Now, if you look at this, you got 3 terms. You're looking for the biggest factor that occurs in any one of those 3 terms. Now, you're almost always factoring 2 things when you factor. You're factoring the numbers and you're factoring the variables. So first of all, look at your coefficients. Negative 12, negative 10, and negative 4. What is the greatest common factor of negative 12, negative 10, and negative 4? Negative 2, right. Now, you could argue, well, why do you need to factor out the negative sign? Technically, you don't have to, but usually, if we've got an expression with a lot of negative terms, we factor the negative out. That's not a rule. It's just a general pattern. So we can factor out negative 2. Okay? Now, when you do that, you're going to be left with what? This term, when you factor out negative 2, the coefficient is that's left is 6. Here, you factor out a negative 2, and you're going to have positive 5, and here you factor out a negative 2, you're going to have positive 2. Good. The negative sign will go out front, and we're going to be left with positive 2. Now look at your variable factors. xy, x squared, and x cubed y to the 4th. What's the greatest power of x common to all of them? Just 1. We can pull out 1x. Now, what does that leave us for x's here? None. Here? 1 of them, and here, 2 of them, squared. Okay, and y. What's the greatest power of y that we can factor out of all of them? Can't do it. There's no y term here to be factored out, and so we have to leave it just the way it is. There will be a y there, there's none there, and there's y to the 4th here. So it's factored. Negative 2x is our greatest common factor. I just wasn't done yet. There. Now I'm done. X squared. That. Okay, so we're done. We factored it. Greatest common factor. Yeah, it's not bad. Now, I'm going to show you two cases of greatest common factor that tend to cause a little bit more problems. Here's one example. 15a plus b cubed minus 25a plus b to the fourth. So we have 15a plus b to the third minus 25a plus b to the fourth. Well, first of all, look at your numerical factors. What's the GCF for the coefficients? 5. We can factor a 5 out. Now, I'm going to avoid confusion with parentheses here, I'm going to use a set of brackets to indicate what we're leaving in the binomial. Now, you've got this factor of a plus b. Here's a case where a factor actually has two terms, but the parentheses lump it together to make it a factor. How many a plus b's can we pull out as our greatest common factor here? You got 3 of them here, 4 of them here. We can pull 3 of them out front. So what does that leave you in this first term? Anything else? That's it. It's just the 3. The a plus b's all went out front. What about here? Yep. Five times a plus b. Well, we can simplify that a bit in your book, and it's good practice to simplify this just a little bit. We can't simplify this anymore. This is 5 times a plus b cubed, but we can simplify this just a bit. Now I'll represent those brackets with parentheses. What have you really got left in here? 3 minus 5a minus 5b. Why did we put that 5 back in? This is all one factor, right? It's all lumped together. Since we couldn't pull the 5 out of everything, we'll just leave it as it is. We wouldn't factor it out partially like we did, or like it's shown here. We'll put that back together and we have our individual factors. That's factored completely. Okay, well, let's just pull out the greatest common factor. What is the greatest fraction that we can pull out of all 3 terms? What's the greatest coefficient? 20, 24, and 36? 4. That's the biggest numerical factor we can get out. And the c squared in the denominator, we can get those all out. A's? Just one a. B? Can't do it. Okay, so then the question is, well, what's left? The first term, we're left with 5. Our a went out front. The b to the 5th are still there. Over 1. I'm just going to put that there to clarify it, but it's gone. It's just over 1. Minus, next one, 6 a squared. B to the 3rd, they're all still there, over c, and the last one, 9 a over c squared. So that's it. It's factored. When you write this, it would just be unnecessary to put that over 1. So we have 4a over c squared times 5b to the 5th minus 6a squared b to the 3rd. There we go. Factored. Greatest common factor. Okay, that one look good? Okay, let's look at the 2 other cases here that we want to explore today at least. Anytime you have a 2-termed expression where both terms are perfect squares, it can be factored into a difference of squares. Well, there's 2 things to watch for: numbers that are perfect squares and powers that are perfect squares. Well, we can factor those into a squared. If a squared minus b squared, if that's the form, we can factor it into a plus b, a minus b. So let's look at a couple of examples of this. First of all, 25x squared minus y squared. Well, you got to ask yourself, what's the first question you need to ask yourself here? is a trick question, incidentally. What's the first thing you got to ask yourself? Ah, good. You ask yourself, is there a greatest common factor? Is there a greatest common factor? If so, get it out front before you do anything else. There's not, okay? There will be in the next example. There's not here. So then we just need to ask ourselves, is the 25 a perfect square? Yeah. The coefficient here is actually 1. Is 1 a perfect square? Yeah. So the numbers qualify. Now, do the powers on the exponents qualify? How can you tell a perfect square variable? Even number. Right. If it's x squared, it's x times x. If it's x to the 6th, it's x to the 3rd times x to the 3rd. If it's x to the 7th, it's not a perfect square. So these have to be even powers in order to be perfect squares. So we can then factor this. This will be equal to, basically, this is playing the role of a squared, and this is playing the role of b squared. So what's your first term in each one going to be? 5x and 5x. Now when we multiply these back together, we'd get 25x squared. That's what we want. And then, of course, the last terms here have to be plus and minus. Got to have opposite signs, and y. Then you always want to check, just to make sure, can either of these two be factored? No. Okay? So we're done. Now, it's a good practice to get into. We won't do this for all the examples today because it would take too much time, but it's always a good practice. Factoring problems, you always know if they're right because you can multiply them out. You better get the original expression. We won't do that for all of them, but we'll do them for a few of them. If we remultiply this, we get 25x squared. Basically, we're foiling to check. 25x squared minus 5xy. That's our outside term. Inside terms, plus 5xy. That should answer the question if there's any doubt in your mind why these have to be opposite signs. That should tell you what do the opposite signs do to the o and I terms. They cancel each other out if they're opposite signs. The o and I will cancel out. And then finally, your last term is y squared. And so since those will cancel, there it is, 25 x squared minus y squared, and it checks. We're good to go. It checks out just fine. But you cannot factor the difference of two squares if after getting out any GCF, one of them is odd. That's right.
So if that y was 3,
Yep. Yep. If that's a 3, then none of that's true. If it's a 4, then you're back in the game again. If that's a 4, good thing that my x didn't leave a mark here. If that's a 4, then what does this become? It becomes 5x and 5x and y squared. Okay? Aaron. Another good question. What if this was a plus sign? No deal. Will not factor. Because here's why. Do you agree? Do you see why these signs have to be opposites to make your o and I terms cancel out? Well, if these two terms are opposite signed, what's going to be the sign on your last term? No, a positive times a negative has to give you a negative y squared. If that's positive, don't these last two terms have to have the same sign, either both positive or both negative? And if they're the same sign, then the o and I terms will not cancel out. It's a good question. So that's why it's called the difference of squares. It has to be subtraction, otherwise it's no deal. Now, one of the cases we're going to, this is so good. One of the cases we're going to look at on Monday are what if these are cubes. It will factor if these are both perfect cubes, whether it's plus or minus. But that's a messy case. We're going to look at that on Monday. We won't do that today. P to the fourth minus 16q to the fourth. Basically, first of all, what do you check? Greatest common factor. Is there a greatest common factor? No. Right, you can always factor out a 1, but that doesn't do much for you. Then you got to check, are both of the terms perfect squares? Is that a perfect square? Yep. that a perfect square? Yep. Subtraction sign? Yep, so it'll factor, okay? This will factor in too. Yep. P squared and P squared. That'll give us our P to the fourth. Then we got to have plus and minus. Order doesn't matter, incidentally. Minus, plus, plus, minus. And the last terms have to be, the coefficient's going to have to be 4 Q squared and Q squared. How's that look? Good, we're half done. You can do it again. Look at your second factor there. P squared minus 4Q squared. It's a difference of squares. That's factorable. Is that factorable? No, that one we're stuck with. So it's still out front here. We've still got P squared plus 4Q squared. But now this will factor again into, right, these will become P and P, plus and minus, 2Q and 2Q. Now, can any of those be factored? We already asserted that this one can't be factored. No, that's it. So we're done. Okay? That's a good question. Gabe's saying, what if it looked like this? What if we had, for example, a squared minus 7 p to the fourth? Out of luck. Yeah, all you could look for then is a greatest common factor, but it will not factor into a difference of squares. Yep. Yep, that 7's a deal breaker. It's not a perfect square. Good. All right, one more of these, and then we're going to go on to the third case. Factor 5c to the third minus 180 cb squared. Well, this is getting to be a boring question. What's the first thing you do? Greatest common factor. Here you've got a factor of 5 and a factor of c that we can pull out of both of those. So we're going to have 5c, and what's going to be left? C squared minus 5c times c squared minus 36b squared. We got out the greatest common factor. That reveals difference of squares. So we have 5c times c and c, plus and minus, 6b. Then you always got to ask yourself, once you're done factoring, is everything factored completely? It is. We're done. It's factored. Okay. Now, the last case we're going to look at are just general trinomials. Three-termed polynomials. If you have a trinomial, you want to write it so that the terms are in descending order. You remember what the order of a term is? The order is your exponent. So you want to write them in order of descending exponents. So for example, those two trinomials, three-termed polynomials, are written in descending order. 5x to the fourth plus 2x squared minus 8. Highest power goes out to the front. Any constant term or lowest power floats to the back. And that only leaves one for the middle. Those are both in descending order. The coefficient on the front term, the one with the highest power, it's called your leading coefficient. And that leading coefficient is important. That leading coefficient will oftentimes tell you what type of factoring you need to use. And that's what we're going to look at now. Well, there's two cases. When you've got a general trinomial, one of two things will happen. That 5 there, that's your leading coefficient. First thing you do is you try and get your greatest common factor out. Once you've done that, you look at that leading coefficient. It's either 1 or it's not 1. If it's 1, that's good news. That means it'll be fairly easy to factor just by looking at it. If it's not 1, you have a little bit more work to do. So let's look at the first case when that leading coefficient is a 1. That's what we'll start with. If the leading coefficient is 1, then we just figure out what the factoring is by looking at it and running some numbers through our head. And we're going to look at a case of that in just a minute here. Okay, let's look at this case. X squared plus 6x minus 16. Now when you go to factor, we're going to factor this in the 2 binomial. There's 2 criteria that have to be met. Well, there's several, I guess, but there's a couple here. In this case, there's clearly no greatest common factor, so we move on past that. It's clearly not a difference of squares because there's 3 terms. Okay, so that means we're going to try and factor it into 2 binomials. Now, you know that the first term in each binomial has to be what? Because of the f in FOIL. They have to be x's. Because when we go to FOIL these back together, we have to get x squared. Okay, so they have to be x's. There's no doubt about that. Now, here's the 2 criteria that have to be met. We want to find numbers to fill in these last 2, and what 2 criteria do they have to meet? They have to what? They don't have to be a multiple of 6 and 16. We have to be able to take, when we do an FOIL, we're going to first, outside, inside, last. These last 2, they have to multiply together to give us negative 16. Your last 2 terms have to have a product of your constant, or the C term in your trinomial, your last term. So these 2 spots have to have a product of 16. Yep, they have to have a product of negative 16, and because of the O and I in FOIL, they have to add up to 6. So they have to product of 16 sum of positive 6. So what you start doing, you start running numbers through your head. You're looking for factors of 16. How can you break up negative 16 into 2 numbers that will add up to 6? Well, 8 and negative 2. You can try different combinations. Whoops, not negative 6. You'll be able to do this mentally if you can't already with just some practice. Negative 16, we could break that into negative 8. We could break it into negative 4 and 4. That's true, but do they add up to 6? No. We could try 1 and negative 16. They multiply together to give negative 16, but they don't add up to 6. We could try negative 8 and 2. They multiply to give negative 16, but they don't add up to positive 6. But 8 and negative 2 add up to 6 and have a product of negative 16. There they are. So x positive 8, negative 2. And it's factored. Product of negative 16. They have to multiply to give you the last term. They have to add up to give you the b coefficient. And we're done. That one's factored. Let's factor 3a cubed minus 9a squared minus 210a. Okay. Well, the first thing you got to do, greatest common factor. We can pull out a 3a, and we're left with a squared minus 3a minus 70. Okay, good. Now, that works out nicely because now you'll look at your trinomial that you still need to factor, and it's case 1. The leading coefficient here is 1. That's what you hope for. That being the case, it's not hard to set up the factoring. We know, as long as that leading coefficient is 1, that our first terms have to be a and a. If that's not a 1, then we're going to have coefficients here, and then it becomes a little bit more problematic. We're going to do that next. But as long as it's 1, you know there'll be a and a. Now, two numbers that will multiply, give a product of negative 70, but add up to negative 3. Yep, negative 70 can be factored into negative 10 and 7. They add up to negative 3, so that's them. A minus 10, a plus 7. Now here again, just to save time, we're not going to re-multiply this out, but we could FOIL this. We could quick check this part of it, FOIL it out, and we get a squared plus 7a minus 10a. So plus 7a minus 10a gives you negative 3a, and your last terms are negative 70. So it works out. And then we could multiply the 3a back in. We better come up with our original expression. Is there any more factoring that you can do here? You always got to check your individual terms when you're done. Make sure you didn't miss anything. No, it's done. Okay, well, I hesitate to even show you this next slide. I hesitate to even do it. But I have to. Not all expressions can be factored. Some of them are prime, just like not all numbers can be factored. If I ask you to factor the number 7, can't do it. Okay, 7 and 1. You can't break it up anymore. Well, the same thing is true with expressions. Now, the reason I hesitate to show you this is because this becomes a favorite answer to factor questions now. Factor this expression, write prime and move on to the next problem. You can't give up that easy. Okay, well, we'd try and factor it. We would say, all right, those first terms need to be x and x. Last terms have to multiply to give 11, but add up to 5. It's not going to happen. Okay, you're not going to find two numbers that will multiply to give you 11, but add up to 5. So, can't be factored. Okay? So, beware of prime expressions. Okay, the last type of thing that we need to look at here is the case where the leading coefficient, that first coefficient isn't 1. They have been so far. If you factor out the GCF and you're still left with a coefficient that's not 1, you have two choices for how you factor it. You can continue on this idea that we've been doing and just use trial and error. That works sometimes. I've seen people who are very good at it. I'm not. A more reliable, though slightly more lengthy process is to use the grouping method. And we're going to look at an example here and do it each way. It doesn't matter to me which of these two ways that you choose, but I would recommend the second one. Let's try this using trial and error. First thing you look for is greatest common factors. Any common factors up there? No, there's not. Okay, so that's off the table. It certainly isn't a difference of squares because there's 3 terms. Our leading coefficient is not 1. Bummer. So trial and error. Trial and error says, well, let's just try and muscle this out. Reason your way through it. What do the first 2 terms have to be here? What? They're going to have to be 2x and x. And the problem is we don't necessarily know which one goes where. This is why trial and error takes a lot of practice or a lot of luck. Okay, now you go over here, all right? So this has to be 2 and 1. Now, with 2, you've only got 2 choices. It can be 2x and x, or it can be x and 2x. But if that's something like a 12, then you could have 6x and 2x. You could have 3x and 4x. You could have 4x and 3x. You could have negative 3x and negative 4x. You could have 1x and 12x. You see the problem with trial and error. But this one's not bad. Now we're going to go over here to the other end, and we kind of do the same thing we were doing before, 12. Now, these two factors have to multiply to give 12, but they don't necessarily have to add up to 11 because this 2 throws a rock into it. Let's just try some examples. So we just trial and error. 12. Give me two factors of 12. 6 and 2. Let's just try 6 and 2. If you're writing this down, write it light. 6 and 2, both positive. If we FOIL this out, we know we get our 2x squared. What do our O and I terms? That's what we have to check. Here our O and I terms give plus 4x plus 6x. Our last term will, of course, give us 12, but does it work? 4x and 6x does not give you 11x. So that's not right. But the bummer is you can't necessarily throw this out. You should switch them around and see if that works. Okay, so we could try not 6 and 2, but 2 and 6. Okay, so 2x times that's 2x squared plus 12x plus 2x. Is that combination going to work? No. Okay, so 6 and 2 aren't going to do it. Other suggestions? 3 and 4. Now, as long as you've got an odd number in here, it must be true that one of these is going to have to be an odd number if you use a certain amount of logic, because no way that these two even numbers were going to somehow add up to give an odd. So let's try 3 and 4. Well, again, we're assuming positive. We know they have to have the same sign because the last terms have to have the same sign in order to give a positive number. And we know they have to be positive to add up to a positive number. So let's try 3 and 4. I don't know, let's try 4 there and 3 there. So now we have 2x squared plus 6x plus 4x. Does that do the trick? No. Are you sick of trial and error yet? Should be getting there. Okay, so 4 and 3 don't work, but what about, got to try the other combination, 3 and 4. 2x squared plus 8x plus 3x. Okay, we hit it. There it is. Plus 12. So this does work out to be 2x squared plus 11x plus 12. That's what we wanted, and so that is the correct factorization. Trial and error is a bummer, but it works. All right? Eventually. And you can use that. That's a legitimate method. Okay, some algebra books, that's the only way that they'll show you how to do it. You just got to get used to it. And once you get used to numbers, doing that arithmetic in your head, it's not so bad. Still, there's a better way, in my opinion. Here's the grouping method. We're going to answer the exact same question, but this time we're going to use the grouping method. This is very systematic. There's a few steps, but there's no guesswork. It'll work every time. Here's what you do. You multiply. It's often called AC factoring because these terms are often, the coefficients are often called the A, B, and C coefficient. You multiply the first and last coefficient together. That's your first step. 2 times 12. So we take the first and the last, they multiply together to give us 24. Now, you do something very similar to how you would have started out in case 1, where the leading coefficient was 1. We want to find two factors of 24 that add up to 11. Multiply them together, and now break it into factors that add up to 11. What two will add up to 11? 3 and 8. 3 and 8 do the trick. So now you rewrite this thing. And you break that 11x into its two parts. So we're going to have 2x squared plus 12. But we break this up into plus 8x and 3x. Make sense so far? Take the product of the first and the last. Find your two factors that add up to your b. Rewrite it. And we're almost done. Now you do something called factoring by grouping. We're going to do a little bit more factoring by grouping on Monday. But you split it right down the middle. You factor the left side and you factor the right side. What is the greatest common factor of these two on the left? 2x. So you pull out a 2x. And you're left with x plus 4. Then you do the same thing on the right. What is your greatest common factor of 3x and 12? 3. Positive 3 specifically. And you're left with x plus 4. If you've done it right, these two will always match. Okay? And now you can factor this x plus 4 out. And you're left with 2x plus 3 times x plus 4, and you're done. It's factored. Okay, so you're pulling this x plus 4 out to the back, and that leaves you with a 2x plus 3 right there. And we're done. It's called the grouping method. No guesswork. Last problem to factor of the day right here. 28x squared plus 24x to the third minus 20x. Now what should you do when you're writing this problem down? Rearrange it. Okay? Or shortly after you've written it down. The first thing we do have to do is rearrange that in descending order. 24x to the third plus 28x squared minus 20x. Okay. Once you've got it rearranged, what are you looking for? GCF. You can pull out 4x. So we're left with 4x times 6x squared plus 7x minus 5. Now, here's a case where we pulled out the GCF and we still have a leading coefficient not equal to 1. So we have to use trial and error. Well, you don't have to use trial and error. You could use trial and error. We're not going to use trial and error. We're going to use the second method. Okay, so what do we do here now that we've got the greatest common factor out? 6 times negative 5. So let's do a little scribble work over here. 6 times negative 5 is negative 30. So we want to find two factors of negative 30 that add up to positive 7. I think I heard it. What is it? Negative 3 and 10. Okay? Negative 3 and 10. There they are. So now we got our two magic numbers. What do you do with it? What do you do with them? You split that up. Yeah, so this becomes 4x times 6x squared. We're going to split this up now. It doesn't matter, incidentally, which order you put them in. It'll always work out. So let's put, doesn't matter, plus 10x minus 3x minus 5. Okay, we split that 7x into those two factors. Now you do what's called factoring by grouping. More on that Monday, but for now all that matters is that we're going to split it down the middle. And keep that 4x out there. We don't want it to get left behind, but I'm going to use a bracket to show what we're doing inside of here. Now 6x squared and 10x, what's your GCF for the left side? 2x. That leaves you with 3x plus 5. What about the right? Nothing, except if you don't factor anything out, will 3x plus 5 match 3x plus 5? You got to get a negative sign out of there so that what you're left with in parentheses will match. So we're going to have to factor out a negative 1. That's often the case where you need to factor out a negative 1 so that the signs will match. 3x plus 5. And we're done. Well, we got to write it, but we're essentially done. So this factors into 4x out in the front times, what's one of our binomial factors? 2x minus 1 times 3x plus 5. And we're done. Factored completely. Beats trial and error. We're not done factoring. We're going to do a little bit more factoring on Monday. We're going to look at a few special cases. But this will cover 90% of the factoring that we have to do.